Hello again. Section 2.1 on the basics of sets. Now, sets is a topic in math that seems so simple. A set is a collection of objects called elements. So why is that so important for math? Well, we talk about a lot of aspects of sets when we do math. And you'll see in a little while how operations with sets is very, very similar to logical operations. Okay? So a set is a collection of objects called elements. And to say that object X is contained in set A, we write X is an element of A. So there's that little symbol that looks like an E. X is an element of A. We name sets always by capital letters. Okay, so if you see a capital letter, that could be the name of a set. But a small case letter will never be the name of a set. If I go X and then that is an element, but I put a slash through it, that means X is not an element of A, of set A. All right? So in the example here, is it true that Monday is an element of B if B equals the days of the week? Okay, obviously yes, because Monday is an element in the set that we call the days of the week. What about February? Is February an element of days of the week? Well, no, so we write February is not an element of B, the days of the week. Okay, so that statement is true. In the example, B was written using a rule. The rule is days of the week. Okay, we could have written B using a roster. A roster is a list by listing out the days of the week with a braces. So B equals the braces, and then Monday, comma, Tuesday, comma, Wednesday, comma, Thursday, comma, Friday, comma, Saturday, comma, Sunday. So that is the roster way of listing the set, just with commas in between each of the items in the list. Okay. It should be clear to you what is meant by, I'm sorry, the video was blocking that. Anyway, so B is Monday, Tuesday, Wednesday, Thursday, etc., all the way to the days of the week. So you can specify a set by a rule, such as days of the week, or by a roster, like the list. All right, so at the bottom of the page it says, it is also clear that what is meant in the following definition. C equals 2, comma 4, comma 6, comma 8, comma 10, comma dot, dot, dot. Now that means you continue that same pattern forever. So it's all the even numbers from 2 on up is that set. Now set builder notation is another way to write a set. Which usually has some rule inside the notation. So for example, this notation here, braces and then X, and then this vertical bar, what that means is the set of all X such that X is a positive integer and X is less than 8. So there's two rules here. The set of all X such that X is a positive integer and X is less than 8. So both of those have to be true. If you use and means both of them have to be true. Okay? In the next example that uses or, but it's still what we call set builder notation. The set of all X such that X is an element of A, X is an element of A, or X is an element of B. All right? So this is set builder notation that really means all the elements that are either in an element of A or an element of B. Okay? This would include elements in both sets also, because the or is not here an exclusive OR. It could be both in both of the sets, okay? Now, there are several commonly used number sets in this course. And when you see the capital N, that's for the natural numbers. Now, I know the natural numbers in other courses or textbooks that you've had in the past probably started with the number 1, not with 0. But in this class, the natural numbers, we're going to start with 0. Okay, so the natural numbers are really what in other courses or texts are called the whole numbers. Okay, so in other texts, 0 is not included in the natural numbers, but in this text it will be. In the second case, the capital Z means the integers. Okay, now I think that they used Z because they were using I for irrational, although I don't even have it listed here, but they're using Z for the integers. Z plus means the positive integers, so that would be the 1, 2, 3, all the way to infinity. Q is the rational numbers. Okay, now they didn't want to use R because R is for the real numbers, but they're using Q. Q, you could think of it as quotient, a quotient of two numbers. Now, rational numbers, the definition of rational numbers are any number that could be written as a ratio of two integers. So that's why in this set builder notation, it says the set of all P over Q, so the set of all ratios where P is in the set of integers and Q is in the set of integers, but Q not equal to 0. So you got to have that specification because you can't have 0 on the bottom. But that's what we call the rational numbers. The word ratio is in there. It just means that you can form, it's equal to a ratio of two integers. Now, capital R is the real numbers. Now, real numbers include both the rational numbers and the irrational numbers, okay? But if you see a plus sign after the R, that means the positive real numbers. So R plus is the positive real numbers. C stands for the complex numbers. Now, complex numbers are all real numbers as well as all imaginary numbers. Now, I don't know if you've taken a class where they describe what imaginary numbers are, but it's just whenever you take the square root of a negative, it results in an imaginary number. But the set of complex numbers includes all real numbers and imaginary numbers. So the complex numbers is a set of all possible numbers. Excuse me. Now, interval notation is something that you should remember from pre-calculus, that to specify the number set, the set of all x such that 3 is less than x is less than or equal to 7. Now, notice that the x is in between the 3 and the 7, all right? So that's what we're talking about, between 3 and 7. Now, it can be equal to 7, as you see that it's less than or equal to 7. So we're talking about anything above 3 and yet less than 7, or less than or equal to 7. So this new notation says basically x is an element of this interval from 3 to 7, but we put that bracket there to mean including 7. But we use the parentheses for the 3 next to the 3 because we don't include the number 3. So my little note here, note that the parentheses are used when x does not exactly equal the boundary number. But the brackets are used when it includes the boundary numbers, okay? So when you use the brackets, let's say we go from A to B with brackets around it, that's called a closed interval because it includes the ends, while AB with the parentheses, as you see here, is an open interval. An open interval, open in the sense that we can't ever reach that number on either side. Okay, we can't reach it. It's still open. You're getting closer and closer to it. But when it's closed, you can reach that number, and that's the very end of it. Now, a set to infinity in that direction is going to be open. Now, here's an example of that. If you want to specify the set here, the set of all x such that x is greater than or equal to 2, that means from 2 on to infinity, all right? So we can say this notation here, bracket 2 comma infinity, but we put an open, a parentheses, because we can never reach infinity. We can never reach infinity, so we use an open parentheses. Now, when we talk about equal sets, basically that means that they have exactly the same elements, okay? Now, really, the same elements, you're going to have not only the same number of elements, but exactly the same elements. Now, we write A equals B if and only if for every x, if x is an element of A, if and only if x is an element of B. Now, what does that if and only if mean? It means it goes both ways. It's a biconditional. So for all x, x is an element of A is the same as or equivalent with x is an element of B. So every time you have an element in A, it's going to be in B, and every time you have an element in B, it's going to be in A. All right. Now, here's an example of equal sets. The set 2, 3, 4 is the same as the set 3, 4, 2. Why? Well, because all the elements in A are in B and vice versa. All right. The same thing with the last set here. The set 4, 3, 4, 4, 2, 2, 3, 2, 2, 3, 3, 3, 4. That still just has the elements 2, 3, and 4. So duplicates don't matter and order doesn't matter. What matters is what elements are in the set, okay? So sets are equal if they have the same elements, and so repeats and the order doesn't really matter, okay? Now, the empty set or the null set, denoted as 0 with a slash through it, or with braces, in other words, a set of empty braces or brackets, that is the set with no elements. Okay, the empty set is the set with no elements in it. It's just an empty set, or also called the null set. Okay, now there's nothing in the null set or the empty set, so that's why we can say for all x, x is not in the empty set. Okay, nothing is in the empty set. So we can say for all x, x is not in the empty set. Now, Venn diagrams are helpful diagrams to show inclusion of sets. What's in a set and what's not in a set. Okay, now this is a simple example. And so I've got set A is the set of all x such that x is a weekday. Okay, now the universal set, when I talk about the universal set, it's a set of all possible objects in a particular situation. Okay, all possible objects in a particular situation. Now, sometimes the universe will be specified. It'll be specified what elements are possible in a situation. Sometimes it'll just be obvious, like days of the week. So the universe, in this case, would be all the days of the week. Sunday, Monday, Tuesday, Wednesday, Thursday, Friday, Saturday, Sunday. Okay? All of the days of the week. So I've got a picture or a diagram of, it's called a Venn diagram. I've got a Venn diagram for this situation. Set A is Monday through Friday because weekdays. Set A is the weekdays. The universe is all the days. So what days are outside of set A? Right, Saturday and Sunday. Those would go on the outside of the set A, but inside the universe set. Subsets. So let's talk about subsets. Set A is a subset of set B, denoted A, and then we use a sideways U, okay? Sideways U with a line underneath it. If all elements that are in set A are also in set B, okay? So, for example, the set of congressmen is a subset of the set of politicians, because obviously there's more politicians than just the congressmen. There's mayors and governors and, you know, all kinds of other politicians. So but it is true that if a person's a congressman, you know, if they're in set A, the congressman, then they're also in the set of politicians, okay? So that's the meaning of a subset. Now, set A is a proper subset, denoted A and then just the sideways U, B with no line underneath it. If A is a subset of B, but A is not equal to B. Now, so what if I said the human beings and the set of people, okay? Is it true that the set of human beings, or well, let's start with the people. The set of people is a subset of the set of human beings? Yes. Everyone who's a person is also a human being, okay? But those two sets are equal also. So we would say the set of people is not a proper subset of the set of human beings. To be a proper subset, the two sets have to be not equal to each other, so that the first set has to be fewer elements than the second set. In that case, it's a proper subset, okay? So like you could say, human beings are a proper subset of the animals, because, you know, you could consider human beings to be in the animal kingdom. All right. Now that depends a little bit on your views there, but let's assume we're going to accept the idea that human beings are in the set of animals. So then it's the human beings is a proper subset of the set of animals, because of course the two are not equal. All right, the next example, in the example in the middle of the page, the set of all mammals is a subset and also a proper subset of the set of all animals, because all mammals are animals, but there are some animals that are not mammals, okay? So proper subset, you got to have some that are not in the larger set. All right, so note, to show that A is not a subset of B, all you got to do is find a single value or object that is in set A such that it's not in set B. So you find an object in set A that is not in set B. For example, suppose we want to show that the set of people who love Elvis, that set of people who love Elvis, is not a subset of people who love rock music. Okay? You just need to find a person who loves Elvis, but who also does not like rock music. And I imagine there are some people who love Elvis, but who do not love rock music. Okay? So let's move on, talk about some theorems about subsets. Theorem 1 says the empty set is a subset of every set. Okay? The empty set is a subset of every set. Now that seems kind of strange because there's no elements inside the empty set. So how can you say it's a subset of set S? So let's consider the statement here. If X is an element of the empty set, then X is an element of set S. Why is this true for any S? Well, we cannot find an element X in the empty set. So in a lot of things with math, it's innocent until proven guilty. There's no elements in the empty set to test this. So it's like false. So that if part of the statement is false. And what did we say was the case when you have a conditional statement, and if something, then something else? What do you say about the whole statement when the first part is false? We said that the statement itself is true, no matter what the second part was. If the first part is false, then the second, it doesn't matter what the second part is. The second part could be true or false. The whole statement, the statement as a whole, is still true. Okay? We said that about if-then statements with truth tables, when we did a truth table. Remember the false row, the rows when P was false were considered true for the if-then statement. Okay? So in this case, it's false that X is an element of the empty set. So therefore, the whole statement, if X is an element of the empty set, then S is an element of S, is true. Okay? So the empty set is a subset of every set. Okay? B, every set is a subset of itself. And this is pretty easy to get based on the subset definition. Okay? Why can we say any set is a subset of another set? Well, if an element is in that set, then it's going to be in that set. So if it's in set S, it's going to be in set S. And that's the definition of a subset. If it's in set A, then it's going to be in set B. Well, since set A is the same as set B, well, duh. If it's in set A, it's going to be in set A. So A is a subset of A. Or in general, S is a subset of S. So we have shown in Theorem 1 that the empty set is a subset of every set, and that set, every set is a subset of itself. So every set is going to have at least two subsets, the set itself and the empty set. So keep that in mind for future material here. Every set has the empty set and the set itself in that set. Okay, or as a subset of that set. Okay. Now, there are some things to look at on page 124 and 125 using set notation with quantifiers and true sets and quantifiers. So take a look at page 124 and 125. Now, let's talk more about this subset idea. What happens if A is a subset of B, but also B is a subset of A? What if each is a subset of the other? Is it possible? Okay, so what would that mean? That means if an element's in set A, then it's in set B. But the other way around means if it's in set B, then it's in set A. You know, if I say B is a subset of A, that means if it's in B, then it's in A. Well, if it goes both ways that way, then it must be that the two sets have exactly the same elements. The two sets are exactly the same because they have the exact same elements. And so really that means that set A equals set B. All right? So if A is a subset of B and B is a subset of A, then A will equal B. And this is how we know that two sets are equal. Okay? So let's look at an example. Note, sets may have other sets as members. Okay, let me talk about the fact before we look at that note. Okay, so let's say that in a particular state, if you have a driver's license in that, I'm sorry, in a particular county, if you are issued a driver's license in that county, you automatically are granted library access in the county, okay, automatically. So the set of people who have driver's licenses in the county and the set of people who have library access in the county, they're exactly the same. Because if you have a driver's license, then you have library access. If you have library access, then you have a driver's license. So they're exactly the same. Okay. If one, you know, it's a subset situation. If it goes both ways. The if-then statement goes both ways. Okay. So note, sets may have other sets as members. For instance, consider the sets A equals the empty set, the set with A in it, the set with B in it, and the set with A and B in it. So we see that we have set A has other sets inside of it. It has the empty set, it has a set with A in it, a set with B in it, and another set. So there's 4 sets inside of that larger set, set A. Okay? So let's look at the next thing. B, let's say that B is the set of all X such that X is a subset of the set AB. All right, well, notice these two sets are exactly the same because aren't these the subsets of the set AB with A and B in it? Because we already said that the empty set is a subset of every set, so that's going to be a subset. This is a subset of the set AB because it, you know, the set A, or I'm sorry, the element A is in the larger set AB. The same thing with the set with B in it. B is in the set AB. And then both A and B both are in set A and the set with A and B in it. So each one of these items, these 4 things, is a subset of the set with A and B in it. So that must mean that these two sets are equal. That set A, which has these 4 elements, and set B, which is described by a rule, not a roster. It's not a listing of the sets, but it's described with set notation, a set builder notation using a rule. And that they define the same set. Notice that these sets are equal, A equals B, and that the set with A in it is an element of set A, but actually the element A is not an element of A, of capital A. You notice that? I don't have just A without the brackets in set A. Just A without the brackets is not in set A. Now the set with A in it is an element of set A. The set with A in it is an element of A, but A by itself without the brackets around it, so just the element A, is not an element of set A. Okay? Because set A is a set of sets, not a set of elements. Or the elements of set A are sets. Each of the elements in set A are sets. All right? And so there's a difference there. So it's kind of subtle, but be careful about that. Look at what the elements are. The elements are all sets. That's the empty set. That's the set with A in it. That's the set with B in it. That's the set with both A and B in it. So we don't have elements alone like this A here, is just an element alone. And so we can't say that that element alone is an element of set A. All right, so definition. Let S be a set. If there are exactly n distinct elements in S, so n tells how many distinct elements there are in S, where n is a non-negative integer, we say that S is a finite set and that n is the cardinality of S. So n is just some integer, non-negative, so either 0, in the case of an empty set, there would be 0 elements, or 1 element or 2 elements. So n gives the number of distinct elements in set S. And so we call n the cardinality of the set. And that set is called a finite set because it has a finite number, n, number of elements. And that cardinality is finite. Okay? Now the cardinality of S is denoted by, we put the bars on either side, so it's the sort of the absolute value of set S, or we just say the cardinality of set S. It's also called the cardinal number of the set. So for example, suppose set A contains the letters of the English alphabet. Then the cardinality of set A would be 26 because there are 26 letters of the alphabet. So in the case of the cardinality of the empty set, well, there's no elements in the empty set, so that cardinality is 0. Okay? Now, some sets, you can't count the number of elements in it. So you can't put a finite number. You can't put an integer as the number of elements in the set. So a set that is not finite is called infinite. That is, there's not some integer that denotes the number of elements in the set. The set of positive integers is infinite, as is the set of natural numbers also. Okay? So if you can't put a number because you can't count it, it just keeps going and going and going and going, then it's called an infinite set. And the cardinality is infinity if you want to ask about the cardinality. Okay, so the power set is another important fact in this section. The power set of a set is the set of all possible subsets of set S. Okay, the power set is the set of all possible subsets of set S. So notice the power set is a set of sets. It's a set that contains inside it sets. Okay, so here's an example. What is the power set of the set with the elements $%? Okay, so you've got those two elements. Now, all the subsets of A are the following: the empty set, the set with a dollar in it, the set with a percent in it, and the set itself, the dollar set with the dollar and the percent in it. So remember, every set has the empty set as a subset of it, and that set itself is a subset of that set. So in this case, it's going to have 4. Okay. Thus, the power set for set A is the following set. Now, notice I'm making a set with sets inside it. So the power set would be braces, and then I put empty set, the set with dollar sign in it, the set with percent in it, and then the set with both of those in it. But it's a set of sets. That's what a power set is. It's a set consisting of all subsets of the set S, or the set A in this case. Now, please note that it does include the empty set and the set itself. Okay. All right. So we had 2 elements in the original set A, and we ended up with 4 sets in the power set. Interesting. Let's look at the next example. What is the power set of B equals 7, 8, 9? Okay. All right, so now we have 3 elements in the original set B. So what is the power set? Well, you start off with the empty set. Empty set is a subset of every set. Then you could have the set with 7 in it, the set with 8 in it, the set with 9 in it. You could have the set with 7 and 8 in it, or the set with 7 and 9, or the set with 8 and 9, or the whole set. The set with 7, 8, and 9 in it. You always have that set to be a subset of itself. So how many sets did we end up with? Well, 1, 2, 3, 4, 5, 6, 7, 8 sets. So when we had 3 elements in the set, our power set had 8 elements. Is anybody figuring out the formula that we could use to figure out how many elements there will be in the power set when you have a certain number of elements in the original set? Well, when we had 2 elements in the original set, we had 4 elements in the power set. But when we had 3 elements in the original set, we had 8. Yes, so the formula is 2 to the power of how many elements were in the original set. Okay, 2 to the power of how many elements were in the original set. Okay, so 2 to the second power would be 4 for when there's 2 elements. 2 to the third power would be 8 elements when you have 3 elements in the original set. I'm sorry, 8 sets, 8 subsets when you have 3 elements in the original set. Okay. Now, some strange situations when we talk about these power sets and all of that. What are the power sets for the following? So, solutions. Since okay, so we're asking what is the power set for the empty set? What is the power set for the empty set? Okay. Now, since the empty set has no elements, the only subset of the empty set is itself. Okay. We said that the empty set is a subset of every set, but the set itself is the same as the empty set. So there's only one subset, the empty set. Okay, so the power set of the empty set is just the set with the empty set inside it. Okay, but what's really weird is the next case. This is when you have a set that has what inside it? The empty set inside it. So it's the set with the empty set inside it. So the power set, well, we know that the empty set is a subset of every set, so that's going to be a subset. And then the set itself also. So we have the empty set and the set with the empty set inside it. Those are the two elements in the power set. Okay? Because as we said, every set has for its subsets either the empty set or the set itself. And that's what we have here, the empty set and the set itself. All right. Now, often we want to discuss the order of elements in a collection. To do this, we want to use what's called an n-tuple, which is really an ordered collection of objects. Okay? So we've actually looked at this in pre-calculus or Math 120. Ordered pairs like x and y, that's really an n-tuple, where n is 2. Okay, but let's define it in a more general sense. Definition: the ordered n-tuple, a1, a2, a3, all the way to an, is the ordered collection that has a1 as its first element, a2 as its second element, a3 as its third element, all the way down till an as its nth element, a sub n. Now notice these are subscripts. These are not exponents. They're subscripts, okay? So that's what we call an ordered n-tuple, okay? It's simply a pairing, or it's not pairs unless there's just two of them, but it's a collection of things, a1, a2, a3, all the way to a sub n. So it could be 5 things, or it could be 3 things, or it could be 7 things. Doesn't matter how many there are. So two ordered n-tuples are equal if and only if each corresponding pair of their elements is equal. So what does that mean? Well, a1, a2, ... an is equal to b1, b2, b3, all the way to bn, if and only if a sub I equals b sub I for I equals 1, or I equals 2, or I equals 3. In other words, a1 equaling b1, a2 equaling b2, a3 equaling b3, a4 equaling b4, all the way to a sub n equals b sub n. All right? That's when two corresponding pairs are equal. All right? Now, in particular, ordered two-tuples are called ordered pairs, like the coordinate pairs x, y. Now, generally speaking, pairs, the order matters. In other words, AB is not the same as BA. The same thing with n-tuples. Order matters. Okay? You can't just switch around, 1, 3 is not the same as 3, 1. Okay? So, it's just a fact about n-tuples. You can't, the order matters that's why they're called an ordered collection, or an ordered n-tuple. The Cartesian product, all right, of sets A and B, denoted A cross B, all right, is the set of all possible ordered pairs A and B, where A is an element of A, of capital A, and B is an element of set B. All right, so that's what A cross B means, is we're going to make a pair where we pick something from set A to be the first thing, and pick something from set B to be the second thing in the pair. All right? Thus, A cross B equals the set of all pairs A and B such that A is an element of B and B is an element of B. All right? Little a is an element of set A, and little b is an element of set B. All right? So let's look at an example, because you really can't, see how exactly this would apply unless you look at an example. So for A being $% and B being 789, find A cross B. All right, A cross B means we're going to pick one from set A and pair it in parentheses with one from set B. So $7. We could also go $8, $9. Now notice you stay in that order where you're picking something from A first and then pairing it with something from B. So $7, $8, $9, and then %7, %8, and %9. All right. So you have to also do the second element there with all three of them, 7, 8, and 9. So we ended up with a total of 6 objects. Okay. Now, what would be the formula to figure out how many objects would be in the cross product or the Cartesian product? Well, if you have 2 elements in the first set and 3 elements in the second set, we ended up having 6 elements in the Cartesian product. So obviously 2 times 3 is the way to figure out how many elements you'd have in the whole Cartesian product. Now, what if we had switched this around and said, instead of saying A cross B, we had done B cross A? Would that be the same thing? Well, no, because B cross A, we would have had to pick our first element from set B and our second element from set A this time. So that would be the element or the pairs $7, 7%, $8, 8%, $9, 9%. But these are not the same, as you can see, because order matters in an n tuple. These are not the same. So in general, A cross B is not equal to B cross A. All right. All right. So that ends the section 2.1. Carefully do the homework there and get used to all this terminology and symbolism, and do those. And then section 2.2 will build on that.